I'm sorry, just a second. Hello, everybody. Now what?
You don't have your house adorned, there's just mirrors everywhere, so you can look at yourself all day?
I don't need that, no. Once upon a time, maybe. Okay. In yesterday, the day before, whenever, I put some notes up, which are called differentiability examples. You all got an email about it, I think. Some people here are nodding yes, so I assume everybody got an email about it, in which some of the stuff we've been talking about the last couple of days about the chain rule, I tried to do several kind of examples. Some of them are pretty messy in terms of the length of time it takes to write them. So I thought it was better for you guys to have them available to you written out, so if you're home, it's hard to see this stuff. And so I'm hoping that's much better. I will certainly take questions about it if you have any when you read them and study them. There's also a special implicit function theorem written at the bottom of after example 7. So I give you 7 examples, and maybe one of the things I haven't been doing is talking to the home. Maybe I should talk to you guys. 7 examples to play around with various ways to configure compositions of functions and how you might find them in other places, and why I change them into functions and things, whereas some people leave them as variables. So I tried to mix up the way we did it. Anyway, there's something called implicit function theorem, and that's after 7. And I'm not saying what page it is because the pages I have here are different than the pages that you were given yesterday. So what I did a week ago is I divided the section. You now have 2 sections on chapter 14, and that's really one big section that I have for myself. Okay, and I cut it in half, so your pages start over again, I think. And mine don't. Mine start on page 17, but I don't think it helps you any. So what's the implicit function theorem talk about? This particular one. Now, I'm doing this for n+1 dimensions. So the reason is because we might have a function of n+1 dimensions, and the reason n+1 is because we actually have a function of, say, 13 dimensions. That means 13 variables, but I want to take one of them and make it a function of the others. And what you have in Calc 1 is something like x squared plus y squared is 5 or something, and you say y is a function of x, so you have 2 variables. You make the second variable a function of the first variable, and then you differentiate. That's called implicit differentiation. Okay, well, what I'm doing here, because we might have, if we have 13 variables, we want to write one of them as a function of 12 of them. And so it makes easier notation situation to call the thing we're trying to solve for a different name than the rest of them. We could call it xn+1, but basically what people do is they take something like this and then they make a vector out of the first bunch of them just to make it look shorter. Okay. The only problem with that, in the notes you have, I did not put a bar under the x. And so when you read the notes about this, you'll see f of xy, x is actually in variables. But if you don't make it bold, which out in the world you won't have it bold all the time, if you don't make it bold, you don't see it as a vector, but it is. This is just a shortening device so we don't have to keep writing out this long thing. Okay? And the case that's going on here is we are going to be assuming that we have an equation in this many variables. Now, over here before class started, I wrote, suppose I have a function of 3 variables. That's one thing we can have. We can also have an equation of 3 variables. And we want to learn the difference between the two. I mean, one's kind of a part of the other. This is true for a certain number of things for a general function, okay? And so a circle, for example, x squared plus y squared is 1. We can write that as f of xy equals x squared plus y squared equals 1. or we can write it as x squared plus y squared minus 1 equals 0. Okay, so we can make a function out of an equation of so many variables, and the idea here is to try to rewrite it as a function of lesser variables. Now, the rule in this special function thing here is, suppose that we have a point x naught, y naught. Now, that point is really a vector x naught, so this is n plus 1 variables. Okay, so we have, if n is 12, we have 13 variables here, so we have a 13-dimensional point here. Okay, suppose we have a point where when we stick that into this formula, we get 0. So this is a point on the graph, not of this equation, because when you have an equation like x squared plus y squared is 1, when we make a function out of it, we make it a function of one variable. We have a one variable domain and one variable range. The equation we graph is in 2 dimensions, right? So in this particular case, there's a function here of n plus 1 variables for which, like x squared plus y squared is 1, some points satisfy some equation. So we have a place like this, and we also, according to what I've written, if you've got access to that, and for those of you at home, what I can do is give you access to that. So we will see where that is. So those of you at home can see what I'm talking about as soon as I find it. It's after example 7, I said. So, well, anyway, I don't know where it is. Right there it is. It's on page 4 of the notes I gave you yesterday. Okay, and we're assuming that the partial derivative of f with respect to the last variable is not 0 at x naught, y naught. Under this assumption, then there will be a function, f maybe, something, where we'll have f is a function of the variables x1 to xn. And f of x naught will be y naught. Okay, so that's this y naught here. And in a neighborhood of this point, there is only one function. So what we're trying to do, if I'm in 2 dimensions, we're trying to say, okay, if I'm at this point here, in a neighborhood of this point, a neighborhood is something down here. In the neighborhood of this point, I have a function of x. Okay? Now, since I drew this, where is the place where you don't have a tangent line? Where do we not have a derivative? If I have y equals f of x here, where don't I have a derivative? I don't have a derivative there. Well, if you look at this, this says the partial derivative with respect to the last variable is not 0, which you're going to find out if we had x squared plus y squared is 5 or something. Where is it that the y value, if I differentiate with respect to y, where is this not 0? Every place except there and there. So what you're assuming in this function theorem is that we are not in a place where the tangent line might be vertical, okay? And in this simple function, that happens here and here. Now, when you were doing this in Calc 1, we just went ahead and did it. This theorem is telling you under what auspices you can do it. And what happens is you have to treat this as a function of 2 variables, differentiate it with the one you're trying to solve for, and that is the one that can't be 0 when you differentiate it. Okay? So anyway, that's this little theorem on page 4 in your notes, which you can get in Blackboard. You guys can look at it. I want to do something with it, but not just that one. This is called a special implicit function theorem, and there are other implicit function theorems, of which this is a special case. And so what I wrote up here earlier, just so I have it written, suppose I have a function of 3 variables, and I want to solve for 1 in terms of 2. Now, that's just what we did over here. Okay, so by what I kind of tried to say over there, okay, what are we going to try to assume is not 0? We would want to say, if I differentiate f with respect to the 3rd variable, now I have to have a point where I'm doing this. So I'm doing this at x naught, y naught, z naught. We have a function of 3 variables. We're in 3 dimensions with our domain. We have points in 3 dimensions. Suppose we take one of them, and suppose it lies on the equation of those 3 variables. Now that's also called a level set for a function of 4 variables, because when I have a function of 3 variables and it's real valued, you get a number. This would, if we graphed it, be a 4-dimensional graph. We just can't see it. Okay, so an equation in 3 variables is a level set for a function of 4 variables, a real valued function. And so anyway, we have to assume that the partial derivative with respect to f is not 0. Now, I'm going to try to show you why we have to assume such a thing. Okay?
Why did we choose the second variable?
Sorry. Z, thank you. 3rd variable. I think I said 3rd variable, I just didn't write 3rd variable. Okay. I want to try to, in a sort of a sense of discovery, try to show you why the theorem has this assumption. Okay? So, basically, if I'm trying to change this into something that looks like this, so you only have 2 variables, this becomes a composition. So I'm trying to change an equation, let's say, of 3 variables or a function of 3 variables into something involving 2 variables. All right, now, so what I am going to do here is define a function g, and g of st, I'm changing the letters, and you're going to see why in a minute. G of st is st f of st. Okay, now, what is the differential matrix of G? Well, G goes from 2 dimensions to 3. So the partial derivatives, there's 6 of them, it's a 3 by 2 matrix. When you go from 2 to 3, the number of rows is the range number, and the number of columns is the domain number. And so what I will get here, when I differentiate S with respect to S, I'll get 1. With respect to T, that's the 2 variables, I'll get 0. When I differentiate differentiate T with respect to S, I'll get 0. When I differentiate T with respect to Y, I will get, with respect to T, I will get 1. And down here, I'll get F sub S. I'm going to use S, and F sub T. It's actually the first and second partial derivatives of the little function little f. That's what dg is. And what does this function become over here that I wrote? It becomes f of g of, now, this is of xy. So I've written, by assuming that z is a function of xy, I've changed the general function into a composition of 2 variables. Okay? Now, what is, and you're going to see it in a second here, if we try to go to variables, I don't know if some of you have liked these little arrows and things. If I had w here, and I have x, y, and z here, that's the original idea. When you see w is a function of 3 variables, you write something like this to get the relationship going between variables. And I think you guys probably like that because most people do. Okay? Now, what am I doing? I'm making z a function of x and y. And this is the identity function for the first variable. This is the identity function for the second variable. Actually, it's not identity, it's actually what we call projection. We're taking st and just getting s. We're forgetting the t. We're taking ST and getting T. We're kind of forgetting the S. Those are called projection functions. Okay? If I take a plane and have a point ST up here and forget the T and only keep the S, I'm actually down on the x-axis with the number S. So when you project a ST down onto the S-axis, you just lose the T. When you project it over, you lose the S. And so these are actually projection functions, but I'm going to write them as, another way of saying this, suppose I have S of S equals S of ST equals S, and T of ST equals T. Can you guys see this? No, you guys can't see it at home. Sorry. Why don't you sound off and tell me? Because you just don't sound off at home. Okay. So I'm going to stop the share so you can see this wonderful presentation. So see all the stuff you missed. I'm sorry. You should come to class tomorrow. I'm joking. What?
Should that small z be W?
I don't know.
Z equals to F of.
Wait. I don't know where you're looking.
It's
It's a small
under
W.
the horizontal line.
Here?
Yeah, no.
Under.
Under.
this. That small z, should that be W?
No, yes, it should be W. Thank you. Thank you. Okay. Sorry. Okay, so now, basically I'm just writing a couple projection functions. What I want to do, because it's x going to x, when I differentiate W with respect to x as a function from here, I can write dW dx. And that's this function. But I want to do dW dx down here as well. And they are different. But if I use this notation, the one from W all the way down here will also be dW dx. And you will get confused sooner or later, because we are using the same exact bad notation for two different things, and that's not a good idea, okay? So that's why I changed the S and T here. So what I want to do is I want to change this to S and T so that notationally we don't have a problem. Now you'll think we do, but this is better. In other words, X is S and Y is T. So anytime I want to, I can write X instead of S or vice versa, but I need to only do that at places where I might get confused. Don't do it everywhere because there's no need to do it everywhere. If we're just saying is W as a function of three variables, there's no reason for S and T at all. But if I'm trying to work this out with variables down here, I need to do this, but if S is X, then dx by ds is 1, okay? And ds by ds is 1, because x is s. Anyway, so this is the function s here, this is the function t, and then I got another one, which is the function f. And f, notice, depends on s and t, x only depends on s, y only depends on t. So now, as I said, if you like variables, it's smart to do it that way, where we equate some variables, but I use them in different ways here as to keep myself less confused with bad notation. Okay? So, for me anyway. So, if I do a chain rule, if I want to differentiate, W is a function of three variables. So when I differentiate it, its differential matrix is W sub x, W sub y, and W sub z, because it's for three variables. Okay? So three space into one space. If I differentiate this, what I have officially is df of g of xy, or st, okay, times dg at xy, or st, depending. Now, this dg at xy is this thing I wrote over here. This is the matrix 1, 0, 0, 1, f sub. Now, I have to decide whether I want to write x or s here. I can write f sub s of st. I can write f sub t of st, or I can write x and y, depending. So if I'm going to do this function at st, then I will use st every place here instead of xy. So this will be st here, and this will be st there. Now, what's df? F is a function of 3 variables. Okay, that's this thing here. Okay, now, that is, again, dw and so forth. We're going to have a 3 thing here with the partials of f. So partials of f, 3 of them. Now, one is going to be called x, one's going to be called y, and one's going to be called z. Okay? So, I made a mistake here. When I make this into this has only got 2 variables, the w. Because w as a function of s and t is only 2 variables. And I'm sorry, this should have been, this is not the whole deal. This is only the composed deal. And so w should be w sub s. I'm sorry about that. I'll try to make some notes up or show you better. This is w sub s of st and w sub t of st. Trying to explain this in this discovery mode I'm in I'm finding difficult. Anyway, once I have, w originally was a function of 3 variables. That's still right here. So here, this should be dw dx, if you like, dw dy, and dw dz, because that's the original function of 3 variables. Okay, but we made it into a function of 2 variables. That's why we only have 2 partial derivatives here. Let's see if it works. This is a 1 by 3 vector or matrix. This is a 3 by 2. When you put a 1 by 3 with a 3 by 2, you get a 1 by 2. That's why this is w sub s and w sub t. And now, once I get this all done correctly, you'll see why I changed it to s and t here. I'm using s and t here and x and y for the function of 3 variables. Okay? So, what am I trying to get to? I'm trying to get to what this is. If I multiply this matrix row times the first row, I will get f sub x at g of st, if you like, times 1 plus f sub z at g of st times f sub s. Now, that's what I get by multiplying the row times the column. What is this when I do this, what am I doing? I'm assuming that this actually is equal to 0. Remember, it's an equation that we're playing with. When I differentiate the equation, what do I get? Since it equals 0, I will get these are both 0. So what I get is that this thing I just computed is 0. Now, remember why I started all this. It was try to discover why this is not 0. That was the idea. Okay, so I got this equation. If I'm doing this at some x naught, y naught, and so on, all right, it's 0 because these are the s naughts and y naughts. This is something on the equation. If
Dr. Brady.
I plot this, I'll put the thing on the other side. What I'll have is f sub z of g of s naught t naught times f sub s of s naught t naught equals minus f sub x of g of s naught t naught. Sorry about all the notation. Now, in order to find f sub s, what do I have to do? I have to divide by this. In order to divide by this, it has to be different from 0. So, if
Dr. Brady.
I find a function and differentiate implicitly, with the equation, like you did with x squared plus y squared is 5, if you remember. Okay, if I'm trying to find the function in its partial derivatives, then we have to assume that the derivative of the original function with respect to the third variable at the point we're involved is not 0. Now, I'm going to give you an example of this where we don't have all these letters. Okay.
Dr. Brady, someone has a question.
Yes. So,
Could you repeat those two equations on the right side of the board,
Yeah,
but
yeah.
just
It's hard to
slow down a little bit?
It's hard to see. Yeah. Okay. Where can I put them? Don't know. Okay, so I'm going to put them under here, I guess. When I try to solve at S naught T naught, when you put in S naught T naught, these partial derivatives are 0. And so the first one I wrote over there is f sub x, and I'm going to leave off part of it. It's f sub z, f sub s. Now, this is at certain places, but I don't have room to write it all out here. So when I solve for this, I have f sub z, f sub s is minus f sub x. And I'm looking to try to find f sub s. To do that, I have to divide by this thing here, which has to not be 0 if it's going to work. And so again, the whole purpose of all this was try to show you why this assumption has to be there. Now, it gets more fun. If you think this is fun, it gets even more fun when we want to do this in more ways. I'll show you the next thing. So anyway, the next thing to consider, you will love it, is suppose that I have, let's say, 2 equations. Suppose I have 2 equations in 4 variables, not 1, but 2, that I wish to play with. So suppose I have 2 equations. So maybe I have that circle, except this would be 4-dimensional now. So maybe I might have x squared plus xz plus w sine, not z, uv plus w plus v sine uv quantity squared equals 0 or something. I might have, and I don't have 4 variables here, so I'll make this a y. I might have 4 variables, an equation. Now, if I just have 1 equation, I got a mess. But if I have 2 equations, I might be able to solve the 2 equations. I might be able to solve for 2 equations in terms of 2 other variables. In other words, I might be able to show that u is f of xy and v is g of xy. So in other words, I might try to say, okay, could I solve for u in this problem? If I could, and this one I wrote is pretty easy in this case, at least to begin with, I can take the x and y over to the other side and take the v down here. I'm just kind of playing now. I have the sine of uv squared, so I can take a square root, and this is, of course, just now really playing with symbols. I have no idea whether I'm allowed to do all that, okay? And if I had the sine, then I can take the arc sine. Anyway, this is u times v, and then divide. Maybe I can solve for u in terms of just xy. But what I just did, I'm solving for u in terms of x, y, and v, because you see I got a v over here. So if I try to solve for 1 variable in terms of the other 3, that's what we've just been doing a minute ago. Instead, I want to solve for u and v in terms of x and y. Okay? So how does that complicate things? A minute ago, you couldn't see it at home very well, but a minute ago, you found out that the f sub z couldn't be 0. It came up when I tried to solve the problem. So if I want to change this into F1 of x, y, u of becomes f of x, y, and v becomes g of x, y. So now I have an equation in two variables. Well, again, you probably can't do much, but if I have a second equation also. Now, when you're trying to solve two equations in so many unknowns, okay, normally to solve a thing, if it's a linear system, if I have linear equations, they're straight lines, if I'm in two dimensions. And having two of them is where the two lines intersect. Solving a linear system of 2 by 2, each of them is a line, and then when you're saying what simultaneously solves them, that's asking for where the two lines intersect. Okay? If we up the ante, we're talking about planes and things intersecting. Okay? In this particular case, I don't want to try to describe what it is, but the question is, can I solve two equations in two unknowns, four unknowns in terms of two? Is it possible to get u on one side and everything with x and y on the other side, no v, and v on one side, everything x and y on the other side, no u? And if you have an equation, you can try to do that. Well, you already see I'm in a mess here with one equation. Theoretically is what we need to have. If it's theoretically possible, then we can do stuff. So the question is, again, if I'm trying to discover what assumptions do I make to be able to do such a thing? Well, it turns out that it has to do with something that we're going to talk about. Namely, it has to do with the determinant of a 2 by 2 system not being zero. Okay, so instead of one derivative with respect to z not being zero, it turns out we're talking about when I have two functions, they have four partial derivatives. And it turns out that it's the determinant of four of them. Okay, so I want to try to show you about that somehow here. So rather than do this in general, I want to try to do a problem and try to show you again from a discovery idea where it comes from. Okay, so suppose that I have xu plus yv u squared equals 2 and xu cubed plus y squared and y square v to the fourth equals 2. Suppose I have these two equations, and the problem is to know when I can solve for u and v in terms of x and y near some point. Now, the point in this case is going to be pretty easy, meaning this is an example, and the idea is not to get hung up on calculating a bunch of numbers. Okay, so what I want u is something like u of xy, and I want v to be something like v of xy. So now you can try to do it, but you're not going to be very successful, I don't think. In other words, this is just nasty enough. You're trying to get u on one side and just x and y on the other side, and v on one side and just x and y on the other side. Playing around. Okay. Now you remember what to do with linear systems? If you have 3x plus 2y is 5 and 4x minus 7y is 3, how do you solve such things? You do various ideas. One would be to solve for one of them and stick it in the other and see what you get. You get one answer, then you stick that answer back in the original equation. That's one way to do it. Another way would be to say, multiply this by 4 and multiply this by -3 and add them. And that way one of the variables will drop out and you get an equation with the other variable. And the third way to do it is to notice that I have a coefficient matrix. I can set this up as 3, 2, 4, -7, xy equals 5, 3. This will have a solution if the determinant of this 2 by 2 matrix is not 0. In this case, it's -21 plus 8. That's not 0. So this will have a solution, and I can write the solution down by what's called Cramer's rule. I don't know how many of you say, oh yeah, or how many of you say, what? I don't know. Anyway, so the determinant of a 2 by 2 system comes into play in a linear system. It's actually theoretically the nicest way to solve it. Okay, not necessarily practically, and you don't put this on a computer. You put this on a computer, but not a big system. Anyway, what I'm trying to do here is figure out what you would do to do this. And so, again, if I take these things, if I call this F super 1, it's x, y, u, v, and F super 2, x, y, u, v. Okay, I've got two equations, except I'm going to make them functions. Okay. In other words, I'm going to make functions out of this. So again, I don't have much space. If I would make this -2 and make this -2, now I got two functions. I want to have things so that the point solves the equation. And if you look at 1, 1, 1, 1 here and stick 1, 1, 1, 1 here, if I did it right, 1 times 1 is 1 plus 1 times 1 times 1 is 2, 2 minus 2 is 0. So this point lies on the intersection, because you can try it here too. This point lies on the intersection of these two equations. Therefore, there is a solution of the equations. These four-dimensional things do intersect in some sense. Okay? Fine. What I want to do is say u is u of x, y. So that says 1 is u of 1, 1, and 1 is v of 1, 1, because I want this to be u of x and y, and this to be v of x and y. So I'm trying to make this, cut this down to functions of two variables. And so what we're going to do is just do it again in the discovery. So what I'm going to do is do what you did like in Calc 1. Suppose I replace u wherever you see it by u of xy, and v wherever I see it by v of xy. And I do what I tell people to do in Calc 1. I'm just replacing these things, and I'm going to leave it equal to 2, because when you do this in Calc 1, you leave the equation, and I'm substituting in the function names that I'm claiming exist. All right, so practical problem, no theory and all that. I'm just going to differentiate this with respect to x, y, okay, and see what I get. All right, so if I differentiate with respect to x, I get 1 times u of xy, because it's a product rule, plus x times u sub x of xy. And over here, I'm differentiating with respect to x, so the y doesn't do anything, but the z here is a kind of a mess. Anyway, but because it's 9 after, this will take the rest of the day to do. I suggest you guys do this, try. And you don't forget we got to differentiate the second one, okay? Because now, a couple of ideas that make it fairly easy. When you get some of this written out, what we're going to do is do this at 1, 1. So what you get to do is u of 1, 1 is going to be 1. Once I get the partial derivatives done, okay? So let me, I don't really want to write that all out because I don't have room, I find. So I picked an example that's too long for the board I got. That's my problem. Anyway, when I get the thing written out, set equal to 0, because we differentiate 2 to 0, and I put in 1, 1 everywhere, then I'm going to get a simplified system. And what you get okay? When you do this, finally, what you will get is 3 u sub x at 1, 1 plus v sub x at 1, 1 equals minus 1, and you'll get 3 u sub x at 1, 1 plus 4 v sub x. Sorry, these should be y's. No, okay. Of 1, 1. This is okay. So I'm trying to say this fast. You get this out of this system. If you differentiate this with respect to x, and you'll get these 2 equations out of it when you put in the ones everywhere. Now, what I'm trying to get to, the point I'm trying to make, remember, when we did this linear system a while ago, there was a matrix, a 2 by 2 matrix was a way to deal with this. When I've got this, I'm trying to find these u sub x and u sub y things. These are the 2 functions that I'm trying to work on right here. And notice the unknowns are these v sub x and so forth, and there's 4 of them, okay? But it's 2 and 2, right? Same thing here and same thing there. This is like x, y here. So how do you solve this equation? Because now it's just a numerical equation. This is like x, and this is like y, just like down here. So it is the determinant of these 4 things that is not 0 that has to be assumed in order for you to get an answer. And if I do the thing with respect to y, now if you do this at home, you've got to do the second equation with respect to x. The one I just tried to do and stop, that's this equation up here. How do you get the other equation? You do the same thing with respect to x of the second equation, and that's why you get this one. Then you put in the ones everywhere, and you get these 2 equations. And what you solve for here is u sub x and u sub y. And v sub x. How do you get u sub y and v sub y? You got to start over and differentiate the first equation with respect to y and the second equation with respect to y. Anyway, what you'll learn is the determinants of certain things have to be not 0. Okay? This is all not in the book. The book doesn't use matrices at all. So the problem is you can't see the generalization. You may not want to see the generalization, but once you see how it works, it involves how many equations do you have, how many variables do you want to solve for how many variables, and it involves a big determinant of a bunch of rows of partial derivatives that have to be not 0 in order for the thing to work. So I will be writing out some more about that, but I want to do something else in the time we have left, hopefully. It's about the same idea, but it's simpler. If we have a function of 2 variables, we know about differentiability now. That has to do with a limit, and it's a quotient, and you have f of like x and f of x naught, and f, now we call it df of x naught times x minus x naught, and this would be vectors. This would be like x, y. This should be like x naught, y naught. I'm trying to do this too fast. And so it's x minus x naught, y minus y naught equals 0 with norm of x minus x naught here, whatever. The point is, this top thing here, we have found out is the equation of the tangent plane. The equation of the tangent plane is this idea, and this df thing, that's the gradient or the partial derivatives. So trying to write this out, if I write out all that stuff up there, you're supposed to now understand what I'm trying to say. This is called the equation of the tangent plane, and that's not supposed to be new. Now, in WebAssign and in the book, they ask you to find equations of tangent lines. So what should you do? You take your function, you differentiate with respect to x, you differentiate with respect to y, you stick in numbers because we always do this at somewhere. We're trying to find the equation of a tangent plane at some point. So it's going to be like x naught, y naught. You got to know what the point is. You plug the numbers in, and what you'll get in the end is y. This should be z, sorry. Z is, this will be a number, x minus x naught. This will be a number, y minus y naught. So you might get something like z equals 2 plus 3 times x minus 1 plus 4 times y minus 2. That's if you're trying to do things at 1, 2. And that's the equation of the tangent plane.
Sir, this was in the section that was due yesterday.
I'm sorry?
This was in the
I
section.
can't understand.
This was in the section that was due yesterday.
Yeah.
For the sign.
Yeah.
So can you please extend the deadline?
Maybe. Guys need to work harder. Anyway, the point is, it's not new to us. You should have been able to do this for the last 2 weeks, in my opinion. Anyway, you just find partial derivative, stick in the numbers, write 1 for x minus this is the point. You're supposed to know how to do that, okay? If it were a line, we wouldn't have one of those. We'd have less. For the plane, you have one more, but you have 2 partials instead of a slope. Anyway.
Dr. Brady,
What?
what is your denominator in that limit?
Oh, x, I don't even care. It's a
Okay.
differential. I don't have time for that. That's 2 weeks ago.
Okay,
Okay?
just making sure.
So the point is, it's the numerator that we're interested in because that's what approximates the function.
Right.
And so the tangent line approximates the slope or the whatever in a curve, in a surface is the tangent plane. Anyway, this is what we get. This is how we know how to find tangent planes. I want to try to do something different, which is x, y, z equals 0, what we've been talking about. And if I have a function of 3 variables, I'm also going to have an associated function graph. This is, when you have a function of 3 variables, like an equation, it is a level surface of a function of 4 variables. Now, the function of 4 variables, if it's differentiable, it has 3 partial derivatives. Okay? So it will have an f sub x, an f sub y, and an f sub z. Now, in an equation, if I would try to differentiate this, with this, what I get is a gradient vector. In other words, this f sub x, f sub y, f sub z is called the gradient of the function. Okay? Now, and my problem is I'm running out of time, but that function of 3 variables, the equation of 3 variables makes a surface in three-dimensional space, okay? So I have some kind of a surface. All right? If I would take a point on the surface, right now that's x naught, y naught, z naught. If I want to think of it as a function of x and y, if I want to think of this surface as a function of x and y, that would be when I, instead of x, y, z, I write fx and I write f of x, y like we were trying to do earlier. Okay? Now, but this thing, if it's a function of f, has a tangent plane that I can get if I knew what the function of f was. If I knew that z was f of x, y, if I knew that, I could get this equation of the tangent plane from it. Okay? So I have an equation of 3 variables. If I could solve for z as equal to f of x, y, so if my equation just happened to be x squared plus y squared plus or minus 5 minus z equals 0, if that happened to be my equation, I could easily solve for z. Now I have a function of 2 variables. Just boom, it just jumped out at me. And I can find the tangent plane. I just did, I tried to. Okay? All right. Now, by the implicit function theorem that we just have been talking about, what did I get when I tried to do this? What was the the thing that had to be the case to solve, and I have it written over here still. The f sub z, remember, this thing had to be different from 0, and then we found the f sub s, or the first variable, was a quotient, and the second one's a quotient, and it's 21 after. The point here is that this stuff I did early finds what f sub x is. If I would take this, and instead of that, write f minus f sub x over f sub z, and this one, instead of this one, write minus f sub y over f sub z. Now, these are evaluated, so they're numbers, but if I'm able to solve the equation for x and y, I could use the implicit function theorem to replace the partial derivative by this thing, and this partial derivative by this thing. Now, bear with me just a second. If I would look at that, I have a f sub z in the denominator, it's not 0. If I would multiply it out, multiply it across here, what I would get is f, well, and also there's minuses here. So if I do that and take them to the other side, what I will get is f sub x times x minus x naught plus f sub y times y minus y naught plus f sub z times z minus z naught equals 0. If you do what I said and just multiply out, this is what you will get. Now, these are all evaluated at some place. Anyway, I get these three things added up, give me 0. Now, so what? That's the dot product of things. What that says is that the gradient vector of f is perpendicular to the surface. In other words, the capital F sub x, y, and z give me a gradient vector. They give me the gradient vector, and when you flip those things in front of x minus x naught, y minus y naught, z minus z naught, you get a plane, the tangent plane. We get a second way to compute a tangent plane. If you have an equation of 3 variables, you differentiate the 3 variables with the function with respect to the 3 variables. You get 3 numbers when you plug in the point. Those 3 numbers are a normal vector. And if you put them in with x, y, and z, you get the tangent plane. I'm sorry, it's way over time, and it's a lot to try to say. You ought to try to say it yourself.